My name is Antonio Scontos, and I serve as the chair of the committee that is supposed to test Prashanth today. And this is part of an examination on public defense of his Ph.D. Prashanth is my student under supervision of both myself and Ivan Bartley from Civil Engineering. The title of his talk is on the board. I want to preface his talk by saying that Prashanth has been a pillar, which means the foundation of my research at Drexel. He started in fall of 2010. However, I do know him from fall of 2009, and fall 2009 was the first day of myself at Drexel. Prashanth was at that time a BSMS student, which is a unique invention at Drexel in terms of how we structure students, taking my graduate level course on applied math, in which he excelled, and that was the filtering process for myself to actually pick him as a graduate student, as pretty much 90% of the group in this room. So I would like to mention that again, Prashanth with Kavan, who just defended a few months back, have essentially assisted the growth of an entire division of our lab, that of non-destructive evaluation, primarily using acoustic emission, which is his thesis. And that's particularly important for me, as this was my first inspiration in research when I was 19 years old in a university in Greece. Therefore, this material is a subject of a personal emotional attachment, if you like. Prashanth has spent almost 4 years with us, 4 years, about 3 months, or whatever this is, in September. And he has been very active with a lot more than what he shows today. And that's an indication again of how he grew as the group has grown, as well as our collaborators, friends, family, and everyone around him. But I'm proud today to say that he's in a moment of defense, and I want to stress the word defense because you will have to defend your work in front of everybody. So the structure is as follows. Today we're going to have about a 45 to 15 presentation in which everybody here can have a chance after he's done and after we clap to ask you questions, and feel free to ask as many and as difficult questions you can to his displeasure, I guess, because he wants the easy questions. And then the committee will have to excuse your presence, and so that we have more time with Prashanth, so we can have more fun with him and actually have a little bit more insight about his work. Is there any question about this procedure? We're ready to start? So again, Prashanth, it's been a culmination of the process. I'm excited about what you're going to present, and you're going to have about 45 minutes. I'm going to give you a signal about when I think the time is about. Yeah. Right? Any questions from your part? Without further ado, the floor is yours.
Thank you, Dr. Prashanth. Good afternoon, everybody. Thank you all for being here today. My name is Prashanth, and today I'm going to be talking about my research on utilizing and developing a cross-validated, non-destructive evaluation approach for damage detection using acoustic emission. Before I get into specific details of my research, I would like to give a brief description of the research process. Currently, aerospace structures are inspected every year or two, and between inspection cycles, this leads to unexpected damage mechanisms because of the complex loading phenomenon that is seen during the normal span of an aircraft structure. So this complex loading profile on an aircraft structure during its normal span leads to the development of unexpected damages between periodic inspection cycles. And thus, there is a clear need to shift from the current periodic-based inspection technique that relies on a number of years or a number of flight hours to actually thoroughly inspect an aircraft. So this research aims to develop an acoustic space framework for reliable damage diagnostics with the goal to shift from the current periodic-based inspection that relies on a specific number of years to a condition-based inspection that relies on targeted evaluation of exactly where and when damage happens. This objective is realized by integrating full-field optical techniques such as the DIC and infrared techniques with the prime marking technique of this research, which is the acoustic emission technique. Additionally, novel data fusion techniques are also utilized to combine the different unique features together to reliably flag the presence of damage, with the ultimate goal of actually applying this framework for a real-time onboard damage detection, which can actually detect in real-time regions of critical damage. So this is the outline of the talk that I'll be following today. I'll begin off by giving a brief motivation and introduction into the acoustic emission method. Then I'll talk specifically about the novel acoustics framework that I'm utilizing in this research and show how this framework is utilized for 4 different cases. And finally conclude by highlighting some of the major contributions of this work. As I mentioned previously, the complex loading phenomenon experienced by an aircraft during its normal service life leads to the development of unexpected damages between periodic inspection cycles. A case in a recent example is the mid-air rupture of a Southwest airline in April 2011, when a section of the roof of the aircraft flew off in mid-air, causing massive depressurization. And notably, a comprehensive D-check was performed on this aircraft prior to this incident, and no ominous signs of cracking was detected during this process. Thus, there is a clear need to shift from the current periodic-based inspection techniques to a condition-based inspection techniques that in real time picks up damages and can provide the physical integrity of the structure reliably. Along these lines, Airbus has now developed a future roadmap for structural health monitoring of its aircraft with the ultimate goal of applying onboard sensors to detect in real time the damage diagnostics of its future aircrafts. However, this research is motivated specifically by a 3-year research grant that was provided to us by the Office of Naval Research to particularly investigate and identify the initiation of cracking in metallic specimens. The motivation behind this was driven by the fact that the Navy wanted to find the right cost to maintain their fleets, where they found out that at least more than 90% of the total life cost was associated after the aircraft delivery. Consequently, the Navy also designed the structural health and usage monitoring program with the goal to continuously monitor their aircraft structures and also prevent Navy fleets being retired much earlier than their expected fatigue life. So very similar to the commercial sector, the Navy also wants to shift from this periodic-based inspection methods to a condition-based maintenance approach that provides targeted evaluation and provides real-time information about the integrity of the structure. So in order to realize this condition-based maintenance procedures, there is a need to shift from the current offline inspection to online-based inspection techniques. And for this purpose, we utilize structural health monitoring approaches. So structural health monitoring is the process of applying continuous, autonomous, in-service monitoring of the physical integrity of the structure by attaching embedded or attached sensors with minimal manual intervention to monitor the integrity of the structures. Now, in order to identify certain damages, certain NDT techniques are utilized to provide sensitive information about the damage. But the clear distinction must be maintained between non-destructive evaluation and structural health monitoring. Non-destructive evaluation is typically provides discrete time histories about the damage in the material, while structural health monitoring approaches provide a more continuous time history about the physical integrity of the structure, and thus can be utilized for both initiation and the development of damage. The other difference between the NDE and the SHM technique is that NDE methods are typically carried during offline inspection, while the structural health monitoring approaches are carried during in-service or online monitoring approaches, and thus can provide early signs of catastrophic failure and ensure public safety and the structural integrity. Nevertheless, in either approaches, in order to optimize the damage procedures or the damage process, certain factors must be considered, such as what is the nature of the damage to be investigated, the material type, the structural geometry, the sensors, and also the limitations of the applied technique itself. So some of the commonly seen damages in aircraft structures, for example, in metallic structures, range from crack initiation to crack growth to impact damage and corrosion. While in composites, the prime failure mechanisms range from debonding to delamination or moisture and water penetration and other sort of damage such as impact. Now, in order to pick up these damages, the commonly used NDE methods currently range from visual inspection to ultrasonic testing to thermal imaging to eddy current and also the acoustic emission testing. Now, perhaps among these techniques, acoustic emission testing technique is the only technique that can detect both the initiation and the development of damage in real time, and thus provide a basis for implementing condition-based structural health monitoring approaches. Secondly, acoustic emission can also be utilized in real time to detect the region of damage or the location of damage, which can then be utilized as an intelligent method to utilize other extensive NDT methods to specifically look at certain regions, thus saving time and cost for damage inspection. These solutions range from point to full field inspections, surface to volumetric-based inspection techniques, and also contact to non-contact inspection techniques. So as acoustic emission technique has the potential to shift from the current offline inspection process to an online inspection process, acoustic emission testing is utilized as a prime monitoring technique in this research. So before I actually show some of the specific results that I've obtained during the AE testing of the different materials, I would like to touch base on the concept of acoustic emission. Acoustic emission is the release of transient elastic stress waves that are produced by the material as the material is being stressed due to localized sources such as yielding, twinning, cracking, debonding, and so on and so forth. What is more important to note is that the same acoustic emission testing technique can be utilized in real time to detect both the micromechanisms and the macromechanisms which forms the basis of identifying initiation and the development of the damage. Now, to further illustrate the concept of acoustic emission, I'm going to show you this video that actually shows how acoustic emissions are produced in the material and propagate due to a specific damage source, in this case, cracking in the plate. So you can see as the crack grows in the plate, you can see the release of stress waves, which is the acoustic emission that actually propagates in the medium and can then be picked up by sensors that are either strategically placed at certain locations or random locations. And the waveforms that are detected are of similar characteristics as the one shown here. Advanced signal processing techniques are then applied to extract features such as frequency analysis and other sort of analysis, and hopefully design novel AE damage detectors to reliably flag the presence of damage for real-time applications. Now, the commonly extracted AE waveforms during the testing fall into two basic categories. One is the burst type emission, and the other is the continuous type emission. The burst type emissions have a signature as shown here, with very little activity in the pre-trigger, while the continuous acoustic emission have an AE signature as shown here. Now, based on these extracted AE waveforms, several AE features are extracted using signal processing techniques, and these are some of the commonly used AE features that are cited that are used for different AE analysis. However, in our research, I wanted to go a few steps further and develop both novel AE descriptors and also advanced AE feature descriptors that are reliable to damage detection. So for that purpose, the AE waveform that was extracted during the test were comprehensively analyzed and shifted to the frequency domain using FFT algorithms. So in addition to picking up the peak frequency, other advanced frequency analysis was also performed to identify the frequency centroid. Further, the FFT algorithms were then dissected carefully into 4 specific spectral ranges, and the percentage of energy in each of these spectral ranges was then calculated and seen to be correlated with the applied loading conditions. Consequently, based on these advanced AE analysis, novel AE feature descriptors were then designed based on the relationship of these features and also the relation of these features to the conventional AE features. These are 2 of the common AE feature descriptors that I've designed, in addition to a few more. Now, the other important factor that's supposed to be understood with acoustic emission testing is the actual AE wave phenomenon that happens in the material. To ensure the reliability of damage detection using acoustic emission, it is important to understand how the waves are produced and propagated in the material. For instance, the original AE waveform that is developed, that is produced by the material due to a damage, and the final AE waveform that is picked up by the sensor do not share a linear relationship. In fact, the final AE waveform that is picked up by the sensors is actually a convoluted transfer function of these several different mechanisms. For instance, the initial source AE waveform has a frequency characteristic as the one shown here, but as it propagates in the material and the geometry, is severely colored and affected, which is further affected by the utilized sensor and the instrumentation that is in the test. Thus, the finally observed AE signal is a convoluted function of all these different mechanisms. So, and that is in fact one of the main reasons that make acoustic emission a complex NDT phenomenon, and in certain cases very challenging for damage detection for field applications. So thus, in order to interpret and identify reliably and cross-validate the AE signals that were obtained during the test, a full field optical metrology technique was extensively utilized in this research, which is called the digital image correlation. The digital image correlation is a full field optical metrology technique that measures the full field deformation and strain on the surface of the structure. A spectral pattern is applied on the surface of the spectral pattern, and stereoscopic visions are utilized to correlate images before and after, before and during the loading phenomenon to obtain the final strain maps and the displacement maps. So as you can see, the DIC adds a new visual dimension to the interpretation of the AE signals and can also be utilized to correlate full field mechanical parameters two AE features to reliably validate and interpret the AE signals. The widespread use of acoustic emission has been mitigated due to several challenges, but four of the main challenges associated with the widespread use of, with the inhibition of widespread use of acoustic emission is related to the high sensitivity to noise and also the complex skill required in interpreting and separating the primary or the dominant AE sources in the material. Also, the complex wave propagation phenomenon that I described previously contributes to this major challenge. And finally, the lack of developing reliable damage parameters that can be irrespective of the utilized geometry or even the loading condition and can hopefully be transferred from the lab scale to the field scale is what is missing currently with the acoustic emission testing. So in order to address these challenges, this research specifically designed three objectives to be accomplished. The first one is the design of a novel, cross-validated acoustic space NDE system. The second is the development of filtering, post-processing, and classification algorithms to identify reliable trends that are sensitive to damage. And finally, the identification of failure mechanisms using novel AE damage parameters. The major contributions of this work includes the three following ones that I've shown here. The first one is the unique hardware integration of the full field technique, that is the DIC, with the acoustic emission itself, with in-house developed hardware protocols where DICs are self-triggered based on certain AE indications with minimal intervention, manual intervention. The second is the shift from the conventional AE feature analysis to more advanced frequency analysis and the consequent development of novel AE feature descriptors with the goal to reliably flag the presence of damage. And finally is the use of multivariate data fusion approaches where different features from multiple NDT techniques are combined using multivariate approaches to reliably quantify the damages. The current state of the art of acoustic emission testing falls in these three main categories, which starts from the operational evaluation, the data acquisition, and the data interpretation or the evaluation, and sometimes is also referred to as data mining now. Specifically, the acoustic-based framework that is developed comprises of four major steps. The operational evaluation, which in this stage, carefully designed experiments careful experiments are designed and the loading conditions are determined. The second stage is the data acquisition stage, which is literally the heart of this framework, where unique hardware protocols are developed to synchronize and trigger the full field techniques with the acoustic emission testing, which is now being submitted for a patent application and was provisionally being published in 2013 with those numbers there. The next stage is the data post-processing stage, which involves utilizing advanced signal processing techniques to identify advanced frequency analysis and also correlate them with the different NDT features that are extracted independently from the acoustic emission technique. And finally, the data mining technique, where ensemble pattern recognition algorithms and novel AE feature descriptors are developed to reliably flag the presence of damage. To interpret and reliably identify the AE sources and material, 6 critical steps are taken in this research. The first is the use of modeling of AE acoustic emission waves in materials to understand how the wave propagates in the material and are affected by the structural geometry or other features. Also, the targeted experiments are performed to identify specific AE signatures for damage detection. And then the third step is the use of complementary full field techniques in order to aid and interpret the unknown AE signals that are obtained in real time. The fourth and fifth step include advanced signal analysis that are utilized to extract the sensitive parameters, with the fifth step including designing novel AE feature descriptors and data fusion algorithms to reliably detect and quantify the damage. So the advanced AE feature analysis that were developed and shown previously were then utilized to see if it has the potential to identify and interpret known AE sources in materials. So for that purpose, 4 known AE sources were simulated on an aluminum 2024 plate. The first source was a pencil lead break test, which is actually an ASTM standard to calibrate the AE sensors during a test. So the 4 sensors were placed on the edges of the plate, as you see here, and 3 other AE sources were also simulated during the test. So you can notice the sensors are placed at the same locations throughout all the 4 sources. And the goal here is to see if the advanced frequency analysis or the advanced feature analysis has the potential of separating these known AE sources in the test. The extracted A waveforms from the four sources are shown here. Clearly, you can see that the PLB waveform had the highest A amplitude in the test. But more importantly, it can be seen that the PLB waveform and the EMI waveform have a burst type emission, while the friction and the impact waveforms have a continuous type emission. Now, another thing to be noted here is the pre-trigger activity. It can be clearly seen that signals that have a burst type emission have a very little pre-trigger activity, while signals that produce continuous type emissions, such as noise and other secondary sources, have significant pre-trigger activity associated with them. Thus, it is essential to have a valid pre-trigger activity in order to separate and provide an insight into the potential source mechanisms of the material. Now, in order to understand if the advanced frequency analysis and the features could be utilized to separate the four sources, the waveforms were converted into the frequency domain, and also the frequency evolution of the waveforms were studied using wavelet analysis as shown here. So you can see that the initial packet of the waveform was associated with a high frequency waveform, but as it propagates, we start to see these low frequency phenomena. Similarly, the continuous waveform that was extracted from the frictional waveform seemed to have a much different behavior in compared to the PLB waveform. You can see a constant peak frequency centered around 100 kilohertz, but also you can note a wide spectral behavior of the frictional waveform, which is also very indicative of a noise type of signal. Now, in comparison, the impact waveform, which also had a continuous type waveform, is seen to have a low peak frequency, as you see here, but importantly, it has a very narrow frequency behavior in comparison to the friction waveform. Finally, the EMI waveform is seen to have a burst type emission, and you can see a sharp increase in the frequency analysis as you see here, and you can see how the reflections also share similar frequency characteristics. Now, to investigate if the designed frequency analysis and the advanced analysis can be utilized to separate them, all the extracted waveforms were then carefully analyzed and converted to the frequency analysis, and were spectrally dissected into equal ranges to calculate the partial power analysis. So it was seen that the partial power analysis was indeed successful in separating the four different AE sources in the material, and thus provides the confidence of utilizing these sort of analysis to separate and interpret the AE signals in the material. So this was then utilized to see if these analyses can be utilized to actually identify dominant AE sources during fundamental testing of materials. So for this purpose, mechanical testing was carried out across different metallic materials, and the first test that was performed was with the AC31 alloy, magnesium alloy that was performed. So the compression specimens were tested, as you see here, were tested until failure, but right around the point of yielding, we could see high amplitude signals which were coincident with localized strain bands that were formed exactly at the same time instance where high amplitude signals were detected. So the two independent techniques were seen to be in good sync and agreement, and revealed that this specific phenomenon was activated with this high amplitude. Now, this test was repeated and the same phenomenon was observed. Thus, future test, a test was actually designed to where the test was interrupted based on the activation of this AE amplitude in real time. So this test was specimen was tested, and based on the activation of these high amplitude signals, the test was interrupted. Now, it was seen that right after 6 seconds, we could see a change from the AE amplitude, as you note here. You can see the increase from low amplitude signals to high amplitude signals. What was interesting to note was that the AE waveforms that were picked up before the 6 seconds were very low amplitude and are characterized by continuous type emissions, while the AE waveforms that were picked up after the 6 seconds were much higher in amplitude and also had a burst type emission. Thus, you can clearly see how the wave signatures evolve after a specific time in the load and in the instant, where you can see a shift in the wave signatures. Thus, in order to understand the cause or the reason behind the shift from continuous type emissions to burst type emissions, detailed microscopic analysis was performed on the specimens. So exactly where we have these localized strain bands that were picked up by the DIC, microscopic analysis was performed both on the localized strain bands and outside the strain bands. For example, the region inside the strain band, which is 4, you can see is clearly full of a specific micromechanism called the twins, as you can see here. While the regions outside the strain band, for example 6, seem to be much clear of twins. Thus, you can see how these strain bands were actually indicative of localized micromagnetisms that activated the material. But what is important to see was how the AE wave signatures, which was collected in real time, was also able to track this evolution of the active micromechanisms in the material. Now, in order to see if the advanced frequency analysis can be utilized in order to track this evolution, partial power analysis of the waveforms were extracted and applied, and can be clearly seen after the 6 seconds where we noted to be the activation of localized strain bands. You can see a shift from the higher values of the partial power 1 to a lower values of the partial power 1, while partial power 3 is seen to increase from its initial lower value to a higher value. What this means is that the low frequency signals are seen to decrease after the activation of the twinning mechanism of this material, while high frequency signals are seen to activate and dominate after the twinning mechanism. Thus, we can see how this sort of analysis actually can track in real time the actual evolution of the micromechanisms in the material. Now, the whole goal, though, was to see if this analysis can be utilized to detecting crack initiation growth in the aluminum alloys, as was the objective with the ONR work. So for that purpose, first mechanical test specimens of aluminum 324 were tested in tension, and prior to actually applying a load, ambient environmental conditions were actually recorded using acoustic emission as shown here. So the initial gripping of the specimen did produce an acoustic emission signature that was of continuous type, and also shows great resemblance to the friction waveform that was seen previously with the experimental simulation of the sources. And you can see again that the frequency features are seen to be very similar to what was seen previously. Now, in accordance to the ASTM standard, East 976, PLV tests were performed on these specimens to calibrate the sensitivity of sensors. And it can be seen that the PLV waveforms again have very similar characteristics to the ones that were shown previously. You can see the frequency analysis indeed shows the initial high frequency and the subsequent low frequency. So the mechanical testing of the aluminum alloys was carried out, and it was loaded intentional until failure, as you see here. And what was seen in real time was the AE features that were correlated to the applied loading condition was seen to be very interesting. Right at the point of yielding, you could see high amplitude AE signals being generated, as well as high RMS values being generated. And the signals that corresponded to the high amplitude signals right at the point of yielding had a burst type emissions. These burst type emissions were not seen with the signals that were picked up prior to the yielding. And so again, similar to the AC31 alloy, you can see how there's a shift in the actual wave signature upon the yielding of the material. Now, the DIC was then utilized to actually help us understand exactly the onset of the cracking in the aluminum alloy. And as you can see here, as the strain maps increase and the crack started to initiate, you can see a jump in the AE counts that was picked up both that was in the AE cumulative counts and in the instantaneous counts that were picked up. And this was then utilized to understand that AE waveforms that were associated exactly in this region. It was seen that the AE waveforms that were associated with the cracking were seen to be very similar to the yielding, but had a much higher amplitude and shared a burst of emissions. Now, to see if the AE features can be reliable in detecting damages during fatigue testing of these materials, several fatigue parameters such as energy density, the stiffness, and the strain that were extracted independently from the DIC was correlated with the extracted AE features. And it can be seen that, so as you can see here clearly, usually AE testing during fatigue produce a large set of AE data. And so it's quite complex to understand exactly what each source corresponds to. So the full field DIC parameters that are extracted are then utilized to interpret the AE features that are collected in real time. And this graph here actually shows the zoomed in version of the last few stages, as you can note here. And right as you see that the stiffness changes and the strain changes, you can see the release of high absolute energy signals as well as high AE amplitude signals. So, but what was more interesting to see is how there was an early indications of absolute energy much prior to actually the strains and the stiffness picking it up. And thus, acoustic emission provides an early indication of the fatigue damage in the material. The finally extracted AE waveforms were then compared to the tension AE waveform that was associated with the cracking that was used with the help of the DIC, and can be seen that the waveforms that were extracted towards the end of the fatigue test had a very similar AE wave signature as shown here, and also the frequency analysis was seen to be very, very similar. Now, in order to classify and separate the AE signals that were obtained during the fatigue testing, pattern recognition algorithms were applied to separate them into several different classes, and potentially associate all these different classes into certain sources. So 4 different AE features was utilized, such as the decay angle, the partial power 1, the frequency centroid, and the peak power. These features were then normalized and then transformed to the orthogonal basis using principal component analysis as shown here. Only the first 3 principal component analysis was utilized as these vectors produced constituted 90% of the AE data in the test. Subsequently, statistical pattern recognition algorithms were then implemented, and specifically the k-means algorithm was implemented to classify and separate the different AE signals into several classes. The compactness and the validity of the classification process is evaluated using an R and tau criteria, which actually describes that a small value of R and a high value of tau actually indicates a good separation of classes. Thus, it can be seen here, 4 classes actually had shown a good classification methodology. Now, so the partial power analysis was then utilized to see how these different classes were projected with the partial power 1 and the peak power. And what is important to see here is this same pattern recognition analysis was applied on 2 different tensile specimens as shown here. What is important to understand is it's not important to match the colors between the specimens, but actually identify similar feature characteristics across the specimens. So as you can see here, the blue class, which is the class 2, seem to have very similar characteristics with the class 0, which is shown here, while the red class here, which is the class 0, seem to have a very similar class with that of class 2. So here you can see across the different tensile specimens, you can establish similar AE feature characteristics. Now, in order to put these classes into perspective and understand exactly how these different classes activate in the material, the classes were correlated to the applied loading condition as you see here. And you can see how the different classes are activated at specific load intervals. So initially at the yielding, you can see that the green class, which is the class 1, is seen to be dominant, while prior to yielding, you can see the blue class, which is class 2, was seen to be more dominant and picks up. While the class 2 signal, which is the red class, is seen to significantly increase post-yielding and then dominate the post-yielding behavior. Now, the same pattern recognition analysis was then repeated on the fatigue testing of the aluminum alloys, and very similar AE feature analysis characteristics were identified across the different fatigue specimens. Thus, this forms the basis of developing a robust classification algorithm for potentially identifying the damage sources in these kind of materials, irrespective of the loading conditions. So this framework was then applied to specifically identify targeted failure mechanisms, such as the one specified by the ONR, where it was just to identify the crack initiation in aluminum alloys. So this framework was then applied to reliably identify crack initiation in aluminum alloys. For that purpose, compact tension specimens were designed and were experimentally tested. But prior to actually experimentally testing the compact tension specimens, acoustic emissions were modeled using finite element analysis to actually see how the acoustic emissions are produced due to the crack initiation and see how they actually interact with the structural features and how it affects the actual wave phenomenon itself. So if I can go ahead and play the video, you can see how the acoustic emissions are produced as the crack goes to the material and how it gets affected as it hits or interacts with structural geometries and the boundaries. What was important to see is how the AE waveforms actually had circular wavefronts as seen here. You can see that the AE waveforms does indeed have circular AE waveforms, very similar to the earthquake phenomena that are produced. So the signals that were picked up right close to the crack are plotted here. You can see that the signal that was picked up right next to the crack was seen to have a burst type emission, with the initial packet having a very high amplitude, but upon the interaction of the waves with the pin, you see that the amplitude actually decreases, as you can note here. And this further decreases as it interacts with the geometry of the specimen itself. Thus, this actually tells us that utilizing threshold-based analysis or amplitude-based analysis for reliable damage detection might not be very reliable, because these features clearly change as it interacts with the structural geometry or the features of the material. And so we need to shift from these kind of threshold-based analysis to more advanced AE analysis. So in order to understand how the waves propagate in the material, 5 different virtual AE sensors were placed on the CT specimen, and the waveforms corresponding to the 5 locations are shown here. It can be seen that the initial amplitude that was picked up close to the sensor seemed to decrease as it propagates in the material, and the time of arrival is also seen to increase as it propagates in the material. Now, this is very important to understand how to place sensors and how to understand what the final sensor waveform would look like. But also I want to bring your attention to see actually in opposite to the amplitudes and the time of arrival, you can see that the frequencies actually provide a much more consistent basis as the waves propagate in the material. You can see consistent frequency in behavior as the waves propagate in the material. So, before actually experimentally testing the CT specimens, a preload was applied on the CT specimen, which is about 100 Newton. And at this load, we still could actually pick up a lot of AE activity, and these are actually the noise sources in the environment. However, the AE signals that were picked up during this preload were seen to be characterized by a very low amplitude, as seen here, and two dominant AE frequency regions were identified. Notably, frequency signals between 400 and 500 kilohertz and frequency signals between 100 and 200 kilohertz were noticed. Also, these signals were seen to be associated with very low energy and low counts. So this is actually the video that was picked up, where it was analyzed using the DIC that actually shows the full field strain accumulation around the crack tip, but more importantly also exactly tells us when exactly the crack initiates, which can then be utilized to interpret the unknown and large AE signals that are detected in real time. So if I can just go ahead and play the video. So you can see as the specimen is being loaded, you can start to slowly see how strain accumulates around the crack tip, as you can see here. And with subsequent loading, you can see how the plastic zone increases, and the strain then develops and increases in magnitude, also as seen here. So with subsequent loading, you can see how the strain increases, and as it approaches the peak load, you can see how this plastic zone actually grows as well. Now this full field technique was also utilized to exactly understand when the initiation of cracking happened, exactly the specific load interval, and also vision. This is an actual visual image that was seen by the naked eye during the test. So you can clearly see exactly at a certain point when you start to see the initiation of cracking. So as the specimen is being loaded, you can start to see how cracks were formed, and which was also seen with the full field here. So this was utilized to see how when exactly cracks were initiated in the specimen. So the full field strain maps actually show how the plasticity grows at various points in the load. And exactly at point 5, which is just after the initial load drop, you can actually see the onset of crack initiation. Now this was then utilized to interpret and analyze the AE signals. So the signals that were picked up before the crack initiation and after the crack initiation were then analyzed. What I need to bring attention here is actually this is not an FFT analysis of a single waveform, but actually a weighted analysis of several AE signals that were picked up before and after crack initiation. So you can clearly see with this weighted spectral analysis, there's a shift in the low frequency signals to our high frequency signals upon crack initiation in the material. So this actually forms the basis of actually confirming that frequency-based analysis does provide an indication of the particular failure mechanism in the material. Now, so additionally, partial power analysis were also utilized to confirm the crack initiation in the material. And you can see that the partial analysis that were performed with the AE signals that were collected during the preload activity were seen to be much less than 500 kilohertz, as you can see here. But upon the crack initiation, you can see the activation of 500 kilohertz. Additionally, you can see the drop of the partial power 1s after the crack initiations, while you can see the partial power 3 signals increasing. This clearly indicates a shift from low frequencies to high frequencies that were generated due to the crack initiation in the material. Now, in order to actually confirm that the partial power analysis was sensitive to the crack initiation in the material, the partial power analysis were correlated with independent features that were extracted from the DIC, such as the strain, and the temperature that were extracted from infrared thermography. And it can be seen right at the final stages of the failure. You can see how the partial power analysis is coincident exactly with the full field strain values and the temperature change. And much prior to actually visually seeing the crack initiation, you can actually see early signs of damage using the acoustic emission partial power analysis. So consequently, in order to develop this robust approach, irrespective of the geometry and irrespective of the loading conditions, to hopefully take it from a lab scale for field applications for crack detection, novel AE feature descriptors were designed based on the ratios of the partial power analysis and also the ratio with other features. It can be clearly seen that the signals that were associated with the cracking were seen to fall exactly in the specific region of the damage parameter. So this actually forms the first basis of actually developing reliable damage parameters using acoustic emission. And currently in the literature, we actually don't have any damage indexes that are actually that utilize acoustic emission signals per se. So then, in order to validate the identification of cracking and further quantify the crack growth of the material, features that were extracted from the DIC and the acoustic features were then correlated using multivariate analysis such as the Mahalan square distance in order to detect reliably and quantify the crack growth of the material. It can be clearly seen that the Mahalan square distance, which is based on certain parameters, is seen that is significantly higher as the crack grows in the material and can be utilized to quantify the crack growth in the material. And also, additionally, you can see that there are very little false positive signals. And thus, this can be utilized as an approach for in harsh environmental conditions or field-based application. The next goal was to identify debonding in composite skin stiffener components, which was sponsored by the office, by the NAVAIR project. So in this particular research, acoustic emission testings were performed in addition to the guided ultrasonic waves to identify the onset of debonding in composite skin stiffener components. So initially, the composite skin stiffener components were loaded in a quasi-static manner, as you can see here. The initial loading profile was seen to be very quiet in terms of the acoustic signal, but right around the peak load, you can start to see the generation of the AE signal, which also corresponded to the release of AE frequency analysis, as you can see here. Now, what is important to note is AE signals are seen only at the peak load and not at the unloading or in the initial loading profile, and thus can be indicative of actual deterioration in the material itself. Now, further, the AE waveforms that were extracted at this high amplitude and close to peak load provide a very interesting phenomenon. It was seen that the waveforms had this dual frequency characteristic, as you can see here, which would actually have this initial large high frequency content, and then later on, and had this dual low frequency content, as you can see here. So subsequently, the skin stiffener components were then tested under fatigue conditions to see if we could detect the debonding in it. So in the quasi-static specimens, there was no visual debonding that was identified, but there were a lot of audible signs that were picked up. But in the fatigue testing, we could actually see visual signs of debonding, which actually corresponded to high amplitude A signals as seen here. These are the correlated A amplitude with the initial load cycles that can be seen here. And you can see exactly at the peak load, you can see the release of high amplitude signals. And right when we saw the debonding, you could start to see how we had high amplitude A signals. Now, in addition to detecting them in real-time location algorithms were also employed to actually want to detect exactly the region of debonding, but also more importantly to spatially filter the large AE waveforms that were collected during the fatigue testing of the material. And you can see that the AE waveforms that were collected from this location seem to be very similar to the AE waveforms that were picked up from the tensile test. You can see that the initial waves are associated with the high frequencies, and subsequently they're associated with the low frequency contents. So in order to develop an AE feature analysis that was sensitive to the extent of debonding, novel advanced frequency analysis such as the frequency centroid was correlated with duration and was plotted as a function of the different applied fatigue loading limits, as you can see here. It can be seen that as loading increased, signals that were associated with the low frequency centroid and a high duration was seen to increase with the subsequent loading in the material. So in order to now separate and potentially identify the source associated with the debonding in the fatigue testing of the composite stiffener component, pattern recognition analysis was performed and three main classes were identified. What it can be seen here, the class 0 and the class 1 signal, which is the red and the green, is pretty much active throughout the test. But the class 2 signal is seen to be active mostly during the loading profile of the test, as can be seen here. And further, these class 2 signals are seen to be associated with the low frequency signals, low frequency centroid signals, and high duration, as it can be seen here. Now, in order to understand what perhaps could be associated with debonding in terms of the classes, the AE waveforms that were representative of the different classes were extracted and analyzed. So the class 0 signals had a burst type emission as the one shown here, while the class 1 signals were seen to have AE signatures as shown here. But the class 2 signal was seen to have very similar AE waveform signatures to the ones that were extracted during the tensile and during the location algorithms that were performed during fatigue testing of the material. So in order to indeed validate the onset of debonding and interpret the AE signals, guided ultrasonic waves were also generated to confirm the debonding material. And it can be seen exactly after the 11th load cycle, which is when we saw the visual debonding. You can see that the damage index that was developed using guided ultrasonic features was seen to be increased in the different frequencies as noted here. So the last goal was to apply the acoustic emission testing as a potential structural health monitoring tool for real-time damage detection. Unfortunately, this this approach is now being applied for a different different infrastructure, and particularly a civil infrastructure that was tested in Drexel here, which was actually then utilized by NSF that allowed us to actually go to the University of San Diego based on our results here to actually demonstrate this potential for one-story buildings in San Diego to test them under earthquake-type loadings. So the walls that were tested here in Hess were actually had a 4 meter by 4 meter dimension, so it was pretty large structural scale with the loading actually shown there. The main objective here was to understand the damage development in concrete masonry, partially grouted concrete masonry walls under seismic type of loading. So for that purpose, the DIC cameras were applied and were positioned at a certain distance away from the wall, as shown here, and the acoustic emission sensors were also placed at the back of the wall. So the acoustic emission features were then correlated with the DIC features and further correlated to the mechanical parameters to indeed validate the potential of utilizing them for onboard damage detection. So I'm going to actually show an interesting video of how the DIC actually picks up early indications of strain accumulation much before we can visually identify any cracks in the specimen under the different. So as the wall is being loaded under tension and compression, you can see how the strain accumulates in the medium. So as the wall is being loaded, you can start to see how strain accumulation is seen to pick up in specific regions of the wall. And at this point, we still